Okay, so let's do the second half of what we started last time. So we started the first half of session 40 when we spoke, what was it, 2 weeks ago or a week and a half ago, before the long break. And,
Wait, we spoke last week, right?
well, you were sick the one day, and what was it, Monday? Monday was the tutorial, so we had a short meeting. Okay, so,
Oh, wait. Oh, let me think. Yeah, I was sick on Thursday, so last time we spoke was Tuesday. Tuesday was chem stuff.
yeah,
So it would be Monday.
right, good. So, thankfully we're done with, I won't make slides for tomorrow. You can just walk me through the outline and we can do some planning. And you can decide which parts you want me to say, and we can figure out how much time we want to spend on each of the things, like how much time do we spend on group theory and representations, how much time on the IR spectrum stuff. I mean, you can just decide all that and then offload whatever labor to me that you want. Um,
You're recording, correct?
yes, I am. So
Okay.
good. So maybe I shouldn't talk about our planning stuff since we're recording for our audience of 5 people or whatever. So. Uh, Okay, so since it's been a week, let me just really quickly run through what we did last time, the Act 1, the motivation for the integral that we saw, and then I'll start doing some actual math, not just pictures. Okay, so what we saw last time was that now that we've had plenty of time to speak about the derivative, which is really the first major problem addressed by calculus, we want to shift gears and discuss integration. And the main problem of integration is the question of, given a function, how do you find the area, or as we'll later see, what is more interesting is the signed area, the area under that function between two given endpoints. Finally, the pen starts working. So I want this area under the curve between two endpoints. And then I tried to motivate this last time. One motivation is trying to find a more rigorous definition of what we mean by area, besides the hand-wavy definition often given in geometry. As it turns out, the ordinary integral we'll see here doesn't quite answer this question in a satisfactory way, but it will kind of point the direction to a truly rigorous, meaningful definition of area, volume, and hypervolume in any higher dimensional space. So that's the goal. Then last time we saw a slightly sharper version of the problem statement, which is finding, in this case, I said the first thing you might ask is, can we find for a positive, or at least non-negative function, the area under its graph between two endpoints a and b, which will here be strictly positive since we've assumed the function is positive. But then immediately after that, I said, actually it will make sense to generalize this question slightly, and instead find the signed area where we count the area with a plus sign if it's coming in above the axis, and with a minus sign if it's below the axis. And I'll try to explain later when we get to the fundamental theorem why that makes sense from the interpretation of the relationship between integrals and antiderivatives. This is some accumulated rate of change, so you're increasing here and decreasing here. I'm trying to keep in the sign to tell how much we're changing in which direction. And then towards the end of last time, I said the way that we're going to make this precise is similar to what we did with the idea of a derivative. You approximate the thing you want, which in the derivative case was, I can't believe I misspelled secant as sextant, or sectant, a secant line with no t. We approximated with a secant line and took a limit to make it a tangent line. Likewise here, we are going to approximate the area using these sort of lower and upper sums, which are just rectangles built by chopping up our interval into different pieces and putting rectangles which are supposed to lower bound and upper bound the area in each of those intervals. And our hope is that, kind of a squeeze theorem type argument, we can make these rectangles skinnier and skinnier, so sort of the area, the missing area below and above the rectangles get smaller and smaller, and the true area will be trapped between those two upper and lower sums. That's going to be the goal. So then I motivated the definition last time, which is just some more words which are related to what I just said with the picture. So, okay, I know it was a week and lots of stuff has happened in the interim, so thoughts or questions about the motivation from the last time we spoke?
I have no thoughts or questions.
Okay. Good, okay, so I keep saying this word partition, so I guess we should actually define what a partition is. Okay, so let's do it. Definition: you fix 2 points a and b that are reals, a is less than b, and we define a partition of an interval, the closed interval from a to v, as a finite collection of points in A to B, one of which is A and one of which is B. Right, so here's the picture. Here I've shown a partition that has 4 points. One of them is A, so that's the left endpoint, and then as you see, one of the points is B, it's the right endpoint, and then I've just put in 2 other points, say x1 and x2. So you just choose a collection of points in the interval so that you have both endpoints in your collection. Now I've shown them as x on this graph, but in what follows it's actually more common to label the points in your partition with the letter t and a subscript. So it's often very convenient to just order the points in your partition from lowest to greatest. So we'll always put t0, the left one, since we know the left endpoint has to be in it, we'll always make that t0, and then there's a t1, which is here the x1, maybe a t2, t3, blah, 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 to tn, and tn is the last one in this partition, which we'll say is the right endpoint b. So it's no magic, it's just saying take a collection of points in the interval. Okay, that's a partition. Now, for somewhat more involved definition, I think there's a picture on the next, so there's a picture which will make this all clearer. But we're just now trying to go back to this picture. So this picture where we had the lower bounding rectangles, see all of these dark gray rectangles are supposed to be below the total area under an interval. So you might ask, okay, how do I get a rectangle whose area is supposed to be strictly smaller than the area of the function on this interval? Well, it's pretty easy. You just take the infimum, the smallest value of the function on that entire interval. So I'm just marking on each of these intervals the smallest value that the function achieves, and I'm marking those in pink. All right, so you can kind of just see, I've looked at each of these intervals, from t0 to t1, t1 to t2, blah, 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 and marked the lowest value of the function in pink. Likewise, you could go through and say, all right, I'm going to mark the highest value. Well, the highest value on the first one happens to be the lowest value on the second, but you see what I'm doing. I'm marking the highest value on each of these intervals in blue, and I'm using those to find the height of the upper bounding triangles, right? Rectangles. So that's the idea of the lots of math that's on this slide. Okay, so let's just do it. Again, so suppose f is, we assume it's bounded, so it doesn't go out, run off to infinity anywhere. It's bounded on the closed interval a to b, and we have a partition, which again we've just defined. It's a set of points that are all in the interval, and where the left one is a and the right one, say, is b. And now we just define these two numbers, lowercase m, so we use lowercase for the little one. This is the infimum, which is the smallest value of f. Smallest value of f on the interval I. So notice this guy comes with an I subscript. So there's going to be one of these for each of the little sub-intervals of the partition, right? So each of these says take all of the f of x's with the property that x is between t sub I minus 1 and t sub I, right? Actually, this is wrong, so I think it should be less than equal to. But the point is you take all of the x's on your sub-interval between 2 points in your partition, and then take the infimum, the greatest lower bound of all of those. Similarly, the capital M's, you just take, again, all of the f of x's on one of these intervals between a t sub I minus 1 and a t sub I, and you take the supremum, so the least upper bound of all of those function values. Okay, well that's, I mean, maybe it takes a little bit to write, that's a long expression, but I think the idea should be hopefully pretty clear. You just chop up an interval into pieces, and then you take the infimum and the supremum, so a lower bound and an upper bound for the function on every interval. Okay, then what? Well, then we want to define the two sums I showed you in that picture. So remember the dark gray sum with all of the lower bounding rectangles. So this was the dark gray. The upper sum was the light gray. So the lower sum is just going to be, and now you know how the sum notation works, so hopefully this isn't too magical. We're just saying go to every subinterval, all of the t's, and you multiply this m sub I, which is, this is the height of the rectangle. And then, of course, since the t's are points on the x-axis, right, these are a partition of the interval a to b, so this is the width of the small dark gray rectangle. right? So this lower sum is just saying go through, take all the lower bounds and multiply them by the widths and add them up. Same thing for the light gray big rectangles. You just take the height again times the width. So you add up all the areas of those big rectangles. Okay, so again, maybe perhaps looks superficially, or at first glance, it looks a little intimidating because there's a lot of big expressions. But what do you think is the idea and the motivation clear, or do you have questions?
This is all perfectly clear. I will tell you when things start to get distracting so I don't make a screw up like I did on limits.
Make a screw up. What do you mean by a screw up?
Thinking the wrong thing for basically 4 weeks and then never really correcting it.
Ah, okay. No, I think you've gotten much better at detecting confusion, which is good. Um, that's something that every student has to go through, right? When you're in high school, the signal you use for yourself for whether you're understanding is, do I feel confused? But often you don't feel confused just because you're not asking yourself enough questions, so you're not understanding, but you also don't feel confused, so you think you understand. So I don't know. I think a lot of people do that. It takes a while before you kind of get over it, but I think you've gotten past that point, thankfully, so we're in good shape. Okay, so let's test this with a little challenge. So I've plotted the function. It's hard to tell what the intercept is because the scale on the y-axis is so big, but this is 1 down here. So this is the parabola x squared plus 1, right? So we've got some nice points. At 1, we have 1 squared plus 1 is 2, and at 2, we have 2 squared plus 1, which you can see is 5, and blah, blah, blah. So it makes sense. So I will ask you, what are the lower sum for, let's call this partition P, I guess. I should give it a name. This is a partition again, so it's a collection of points, with the left point being 0 and the right being 5. So our notation is the lower sum of the function f in the partition P. And what should I add up to get this guy?
Okay, so we are going to be adding up I'm going to say width between our partition. How do I properly word it? I guess partition points is consistently 1.
Yeah,
so
good.
We're going to have 1 times f of 0, f of 1 minus f of 0. Begin parenthesis, of course, don't forget it.
1 times, so wait, why f of 1 minus f of 0 again?
Allow me to recall.
Yes, I think we're
Right. Never mind.
So we're supposed to take the lowest. So like for the dark gray ones, you say what is the lowest value the function hits on this interval, and you multiply by that guy for the partition.
Okay. Right. So, trying to remember the proper. Is min defined using both a function and a range?
Yeah, so you can define a min. To be totally precise, we should use the infimum rather than the min, because they're,
Right, infimum.
yeah.
Applying different words that aren't totally correct.
Good, so you say we want 1 times the infimum of f on this interval, right? So what is that? So that's the height of the green rectangle. So what is that infimum for this function?
So that infimum is going to be 1.
Good. Okay. Then what's the next piece?
We see that we're going to have, once again, a width of 1 times, in this case, a height of 2, since 2 is the infimum of f of x on the interval 1, 2.
Good. So now you're seeing the pattern. Since this guy's strictly increasing, the infimum's always going to be the left endpoint, right? So that's helpful. But okay, good. So I agree. That one is 1 times 2, and then what are the rest?
It's going to be 1 times 10, and then wait, give me a sec. Incorrect. 1 times 5
Yeah, about that one.
plus 1 times 10 plus 1 times 17.
That looks good. Yeah, 1 times 17. So I don't know if I really want to add these, but I don't know if I can even do the arithmetic correctly. Why did I
1
write?
plus 2
Oh my god.
equals.
Uh, bad, bad, bad. Okay, 5 plus
You
10.
can do it.
Arithmetic is hard. This is 8 plus 18 plus 17. Is that 35? Maybe. 38.
27, 33, 36,
Did I do this right?
32. Okay, that's right. Never mind.
Okay, good.
I thought 27 plus 5 was 33 for a minute.
Dude, arithmetic is challenging. Okay, so now when we do the upper sum, we'll use the supremums, which is the height of the red rectangles, right? So what is this sum?
So once again, we have a consistent width of 1, but in this case, the supremum of f on the interval 0, 1 is going to be 2. So we're going to have 1 times 2 plus 1 times 5 plus 1 times 10 plus 1 times 17 plus 1 times 26.
Good. So I'm just going to cheat a little bit and notice that this sum is almost the same as this sum. If you subtract off the 1 and then add on a 26, is that right? So
Yep.
if I did that, I would subtract off a 1 from this, give me 34, and then I would add a
26 to get 50.
Yeah, is that right? That sounds
No,
right.
60.
Oh, 60, good.
Yeah.
Good.
Oh.
Looks, is that even right? So 7, 17, 34, 60. Yeah, okay, good. Alright, so let's just do some sanity checking. One, the lower sum better be less than the upper sum, just graphically and by the definition. Infimums should be less than supremums by definition, so that is true. We can see that we used a fairly coarse partition. By coarse, I mean the difference between adjacent points is fairly large. One is pretty big. So the difference between these is also quite large, but at least they will lower and upper bound the true area respectively. And hopefully it's intuitive that if I chop these into, say, smaller ones with a half, or even smaller to a tenth or a hundredth, and added those all up, which I think I'll ask you to do in Python, to write a function that'll just go through and chop up this guy into as many pieces as you want, find well, approximate the supremum and infimum by just looking for big and small points, and add them all up, and then you can see explicitly with your algorithm how they'll converge to a true area, which is sometimes called numerical integration for obvious reasons. Okay, thoughts on this fairly simple-minded example?
Numerical integration implies that there is an algebraic way to do this.
Yeah, so we will actually see that there's a way to just write down the exact answer, and then you can compare your algorithmic case to the exact answer, which we can do in this case, which is using the fundamental theorem of calculus. You just get the exact answer in one step. I mean, you don't have to do any work. You just look at it and write down the answer.
Darn, you aren't receiving Slack messages while you're streaming. That's good, because I wrote down wow.
Well, if you look down here, you can see there's a blue bubble, so I am receiving messages, but I muted it, so it only appears far right. Oh boy, alright.
Big stuff.
Good. Okay, let's just build some intuition. So we don't have to calculate here, but I'll just ask you to tell me what you think and explain any reasoning you have. So first, the slightly easier one. Let f be any function, p be any partition, and say we compute the lower and upper sum of f using that same partition p. So we take L of f in p and U of f in p. What is the algebraic relationship you expect between these two?
It should be the case that L of fp is less than U of fp.
Good. I'm going to press you somewhat. Can it ever be equal? Is it less than or is it less than equal?
Think about a line.
Yeah, so you say take a constant function, right?
Yeah.
Yeah, so if you take a straight line from A to B, then the lower sum and the upper sum, well, the supremum and infimum are the same because it's constant, so it can be equal. But good, good. So indeed, you're right. The lower sum is always less than or equal to the upper sum. Now let's think a little harder. What if we take two different partitions, P1 and P2? So they can be different points. So maybe I just chop up the interval differently, or maybe they have some of the same points, but P2 has more of them. But if they have different partitions, what do you think in general would be the relationship, or do you think there is a relationship? So do you think there is a relationship between them, and if so, what is it?
I believe that there is absolutely no relationship, at least guaranteed.
Yeah, good. So for a general function, there will be no relationship between these necessarily, I think. Um, yeah, if you have a lot of weird jumping around or discontinuity, I don't think we can even. Is that true? Actually, well, now I've confused myself because I'm just thinking about nice continuous functions here. But okay, I think it might be true that for general functions, this is still less than or equal to, but I'm not sure, actually. Okay, well, good. I like the
What if
skepticism.
the upper bound? What if P2 is in the negatives and well, what if P2 is in then call negatives and with negative results?
P2. Well, the problem is that maybe I should be a little more explicit. So, what if P1 and P2 are partitions of the same interval? So, it's still A to B, so they still cover all of the same area, but maybe they just chop it up differently. So I'll do one green partition, which looks like this, and then I'll do a separate, maybe this orange partition, which maybe has, I don't know, it's different like this. I chop it up in a very different way. So maybe this guy has a huge area here. So in the orange partition, I would say, all right, maybe the max or the infimum, supremum on this big interval's over here, and the infimum's over here. But I think it might still be true that if it's a partition of the same interval, that you're going to get the idea that the U is going to be at least as big as the L. Can you maybe I'm wrong. Do you have a counterexample? Maybe you're thinking about something that jumps around a whole
Maybe.
lot. What'd you say?
Let me think. You simply said that P1 and P2 are subsets of AB.
They're partitions, right? So these are both.
Right. So they take up the range somehow.
Yeah, so
I
these
see.
these are both just lists of points, t0 up to tn, such that the lowest point is A and the highest point is B, right? So they're like different tick marks, different ways of chopping up this interval, but they both have to begin and end at the same place, A and B. Um, so I don't know, maybe are you thinking of like a really jumpy function like stars over Babylon or something that might have these guys not obey the inequality anymore? Or did you have something else in mind, maybe?
Well, I think what was the way to do it? It seems like it should be true, but that doesn't mean anything.
Oh, it seems like it should be true that they do still satisfy the inequality, the less than?
Like, I think I'm trying to indirectly quote something that you have said in the past. And I think actually a mistake I made by suggesting that I can't think of any function that would do something, therefore, insert argument.
Ah, yes, the argument by lack of imagination. For instance, why wouldn't Pythagoras for accelerations be true? Good, yeah. So I agree. If we can't think of a counterexample, uh, it might. I mean, if we have no information, then we should be totally agnostic, right? So, uh, if a priori at the beginning you say I don't know if there's any relationship between them, so then
Wait, how would these handle the tangent function?
Good. So I snuck in a word. I snuck a word past you. This word bounded, right? So we only define these for bounded functions. So remember, bounded means there exists some number m such that everywhere on the interval the function is less than m. So tangent is not bounded because it runs off to infinity, right? There's no number m such that tangent is always less than m because it gets a vertical asymptote, right? So in fact, we can't integrate tangent over its whole domain. We can't, well, that's not true. We can actually do it, but I'm not telling you how to do it yet. Right yet, for now, all we're doing is talking about functions that don't run off to infinity like tangent. Good question, though.
I forget, is tangent odd or even?
Tangent is sine over cosine, and sine is odd, and cosine is even, so tangent is odd. Because odd over even is odd.
Does that tell us everything we need to know?
That only tells you about the integral on a domain, sorry, an interval of the form minus a to a, right? Because if it's odd and you integrate over this domain, you expect the integral to be 0 because it cancels by symmetry. But, I mean, we're just talking about any intervals, right? Nobody ever said you had to integrate minus a to a. What if I want to just integrate over this part, right? If I want to find the area under this, and maybe he runs off to infinity here, what's the area under this graph? Well,
Okay, I thought you said over the whole domain.
oh, no, no, no. So we're always on intervals from a to b, right? So remember we talked about partitions, chop up an interval from a to b.
Right.
Or we're back here. General problem we wanted to solve was this thing. If I hand you any a and any b, what's the area under the graph with sign on that interval? So any a, any b whatsoever. Not
And I assume this means wants that interval to be closed.
Yeah, yeah. So we're only going to integrate here over closed intervals. If you want later, I could define how you integrate on. This is why I keep saying domain. I apologize. A domain is a certain type of open set, and we define intervals on open sets by taking the supremum over all integrals over closed intervals contained in the domain, which I can tell you more about later. But for this reason, I often accidentally say over domains, which are open sets, but I shouldn't do that. I'm letting my training bias my language because here we're starting with the easier thing. The easier thing is just closed intervals. So we're only integrating over closed intervals in this chapter.
Okay.
Good. These are good questions and thoughts. Other thoughts.
I have no thoughts.
Okay, so let's come back to this question then. So let's just run through it and let's be very methodical. So at first we say, all right, maybe for a general function, you say I can't think of any counterexamples, but I'm not totally sure. Maybe there's some wacky function you could cook up that would have no relationship between those. That's totally true. So based on that statement, we would say, all right, I'm agnostic. I have no opinion. You say, I have no opinion on whether there's a relationship between these. I can't think of a counterexample, but I mean, intuitively, I would think that L would be less than U's, but I mean, intuition isn't necessarily a good guide here. So let's see if we can restrict scope and see if we can answer an easier question where our intuition might be more helpful. So what if I say not just any function, but I say a nice continuous function. So I take some nice continuous function. So in this case, where we're ruling out all of the counterexamples, you might make the following argument. You might say, well, by definition of infimum, every lower sum between f and p is going to be less than or equal to the true area under this curve, which I've not defined yet, so this is still a sketchy argument, but that's what I was calling R, right, on the previous picture. R of f, which doesn't need a partition, and every upper sum should be larger than that, right? So we would say this is not a totally rigorous answer to the question, but you might think if it's possible to define in a consistent way an area under this curve, call it R, then L must be less than or equal to R, and U must be greater than or equal to R, regardless of what the partition is. So P1, P2. So If that's true, then we might think that there's still a less than or equal to, right? But, but we haven't proven that, so good. So your answer to this question was basically the best that one could have possibly said at this point, because I included this question to signal the fact that we don't really know how to answer this yet. We need to develop more machinery if we want to answer it in an honest, methodical way. So, good. More thoughts on this?
No thoughts.
Okay. All right, so let's do that. Okay, so what were the answers? Well, as you said, in the first case, it's pretty, whoops, less than or equal to P1, whoops. So in the first case, it's pretty easy. You could prove it in one line, basically, since this is a sum of m sub i's, and this is a sum of capital M sub i's, but by the definition of supremum and infimum, the infimum must be less than or equal to the supremum, because the infimum's a lower bound and the supremum's an upper bound, and that's what bounds mean. In the second case, indeed, it certainly seems, if this guy has a sensible area, that we should have this, but we should prove it. So, okay, that was motivating what we're going to do next. So, first, in order to prove this, I'd like to go through a lemma. So this will be kind of the longest and most difficult part of the meeting, is proving this very technical lemma. So, first, I'm going to say, suppose we have two partitions, P and Q, but P is a subset of Q. Sometimes we say, with somewhat more poetic language, that Q is a refinement of P. Why do I say refinement? Because if the pink tick marks are Q and the blue tick marks, so I'm just going to take every other one and then maybe take the B at the end. So the blue ones, I guess it's hard to see what's going on here, but if Q is the partition which has T0, T1, T2, T3, T4, and T5 equals B, and the blue partition only has T0, T2, T4, and T5, so that's, again, P is, just to really beat a dead horse here, if P is those points and Q is all of them, so T0, T1, all the way up to T5, then clearly Q is bigger as a partition. It has more points. Q is a larger partition than P, so since these guys are just sets, P is a subset of Q. But sometimes when I'm speaking informally and I don't want to say P is a subset of Q, because that's kind of hard to parse in a sentence, I will just say Q is finer than P. Why finer? Because if you look at this and think of this like, I don't know, you're chopping vegetables or something, if there's a lot of chops, it's more finely chopped, and if there's fewer chops, like P, then it's more coarsely chopped. So I'll speak of the smaller partitions as coarser, and the larger partitions with more chopping as finer. Anyway, okay, so there's not much going on there. There's just it's me being silly, but okay. Anyway, so back to the lemma. So suppose we have two partitions, P and Q. Q is finer than P. Or in other words, every point of the partition P is also in Q. Then the lower sum of F in the partition P is less than or equal to the lower sum of F and Q. And the upper partition of F and P is bigger than or equal to the upper partition of F in Q. So notice that this is not quite what we wanted to prove. We wanted to prove that the lower sums are always less than the upper sums, not that the lower sums are less in different partitions. So this is only a lemma. It's going to get us part of the way to where we want. But the proof's already going to be kind of hard. So the idea of the proof is we're first going to think about the case where Q has only one extra point than P. Right? So not the case I drew here, maybe the case where you just add 1 point to go from P to Q. And then I'll argue that in the general case, for any pair of partitions, you could just apply a sequence of steps where you just add 1 point at a time to get from one to the other, and apply the results of the previous argument at each of those steps. Okay, so big wind-up, but thoughts, or is the statement we're trying to prove here clear?
I was beginning to ask a question about what something along the lines of, actually, yeah, the question no longer makes any sense, and I can't even say it myself because I don't understand my question.
Can you at least repeat the words you were going to ask, even if they don't make sense?
I already forget.
Damn it, you should have interrupted me sooner. Just shout out over me if you have a question, because I don't want you to lose the thought.
Oof.
Wait, why oof? I'm not being sarcastic.
Oh, I was oofing for myself.
Oh, okay. I thought you were
There's
oofing.
reasons. I don't know.
I thought I did something bad and you were oofing me. Okay. Um, all right, well, if you remember it, you should ask, but otherwise, I will start the proof. So, okay, so as I say, let's think about first the case where Q has just one extra point. So I'm going to label all the points. So P, which is the coarser partition, is going to run from T0 up to Tn. And to be totally general, we have to allow ourselves to inject that extra point anywhere, right? So we can't assume that U is injected at the end if these are in order. I know sets are technically unordered, but just assume that we've numbered these guys so they're in increasing order. So since we have to allow ourselves to inject the extra point anywhere in the sequence, I'm just going to say Q is this other partition where we inject U between k minus 1 and k, where k is completely arbitrary. So k could be 1, where we inject this guy right at the beginning, or k could be like n minus 1, we inject him at the end. You can do it anywhere. Okay, so let's compare the lower sums. In particular, I'll start with the lower sums, so these are the lowercase m's. Start with the lower sums for these two partitions, and let's just look at the interval where we inject the new u, right? So here, the infimum of the function on the old interval, so this is the interval in P, which is from t sub k minus 1 up to t sub k, that guy, this is the infimum in P, which I call M double prime. So we're going to have a lot of primes because there's going to be a lot of letters, but M double prime is, speaking kind of heuristically here, the infimum in the old partition, P. And what I'm going to try to argue is that when we inject a new point U, we're going to have to split this interval into two pieces and think about, okay, what is the infimum of the function on each of those two subintervals? So for instance, here I've shown one of them. When we inject U, now Q asks us, the new partition Q that is finer, asks us, go and look at each of my subintervals and take the infimum. So since we injected a new point U, we're going to get a new infimum, which is just M prime, which is the infimum on the first half, so I guess I should say half of Q's partition, because we also have to look at from U to T sub K, Q's partition. But this is just a picture. I'll actually write the math on the next slide. But, okay, is it clear what we're doing here by injecting this extra U point?
Yes.
Okay, good. So then, what's the actual math? All right, so now we have to do some work. Okay, what do we do? I'm going to... Oh, did I say the wrong thing? Oh, yes, I'm sorry. What I just said was wrong. M double prime, I forgot the way this proof goes. M double prime, it happened to... Well, what I said was actually true, but it's not what I wanted to say. M double prime was supposed to be the infimum on the second half. In this case, it happens that they're the same. So this is the infimum on the second half, U sub T K, and M prime. Yeah, I confused myself. The prime and the double prime ones are both supposed to be in the partition Q, but they're the first half and second half. So M prime is inf on the first half, T sub K minus 1 up to U. So I lied slightly. Well, or I was misleading, but anyway, okay, fine. So we have a new partition Q. We're going to split that piece where we injected U into two pieces and take the infimum on the first half, the K minus 1 up to U, take the infimum on the second half, which is U up to T sub K. Now I'm just going to write the definitions of the lower sums in both P and Q. Okay, well in P it's easy, right? Because if we just define the M sub i's, so remember this is the inf on T sub K minus 1 up to T sub K. Notice we have to do minus 1 because the first one is indexed 0, but this sum starts at 1, so 1 minus 1 gives you the T0. So L is the sum of the infimums, the infima, in the old partition P. how is Q different? Well, now there's going to be several terms because Q injected a new point U. So what do? The first intervals before U are unchanged, right? So I still sum the m sub i's from 1 up to k minus 1 because I inject U at k. So those guys are unchanged. Then I take the infimum on the first half of the U interval, which is the m prime. Then I take the infimum on the second half of the U interval, which is m double prime. And then I do the rest because these guys are also unchanged. So this is the k plus 1 up to n. The other guys are the same as in P. Okay, so these are the two sums we're trying to compare and get an inequality between them. We want to prove, again, that the P guy is less than the Q guy, less than or equal to. So if you just look at these two, if I want to prove that the top guy is less than or equal to the bottom guy, I want to prove this inequality, well, I can kind of subtract all of these sums on the right side and subtract them from the left side as well, and that's only going to leave a single term in this sum. Because notice this sum goes from 1 up to n, and now I'm subtracting from both sides the sums from 1 up to k minus 1 and the sums from k plus 1 up to n. So when I subtract those both off of the left, I'm left with only one term that wasn't in either of those sums, which is the guy right at k, right? Because I go up to k minus 1, I go from k plus 1 up to n, but I miss k. So on the left, what I want to prove is that this term, the leftover term with just the m sub k, I need to prove that he's less than or equal to the two terms left on the right, which are the m prime and m double prime. Okay, if that's unclear, I can write it out more carefully, but do you see the algebra I did there to convert this into this statement?
This is all clear.
Okay, good. All right, so that's what we need to prove, this thing. So I'll prove that on the next slide. It's actually not bad, just have to use what infimum means. Okay, so to prove that last line, we're just going to notice something. We're going to look at the set of all f of x's on the interval from t sub k minus 1 up to t sub k. So if f looks like, I don't know, f looks something like this, like something wiggly, and there's a tk minus 1 up to t sub k, and I chop in with another point u. Well, the set of all of the heights, the y or f of x values, the set of all of those y values on the whole interval from k minus 1 to k certainly contains all of the numbers in the smaller subinterval, right? It's just a bigger interval. This guy has all of the numbers in this guy and maybe some smaller ones. So by the definition of infimum, infimum is the greatest lower bound. Any greatest lower bound on the first set must be smaller than or equal to all of the numbers in this set, which also means it's smaller than or equal to all of the numbers in this set, because this one is a subset of the first. So by the definition of infimum, if this guy is a subset of the first, then the infimum of the first set must be less than or equal to the infimum of the second set, right? So this guy has to lower bound all of these guys, so he's got to be smaller. Good. You could say the same thing. Well, what if I look at the second half? On the second half, same argument. This guy is a subset of the first guy, so anybody who lower bounds all of these guys better lower bound all of those guys. So we also see m sub k must be less than or equal to m double prime. Well, okay, so that's very easy then. Then we just plug those two inequalities into the thing that we're comparing. So you take m sub k times this distance. Of course, just by algebra, I can add and subtract. I can add 0. What I'm doing here is adding 0. How am I adding 0? Just notice m sub k times u and m sub k times minus u. So I've just added umk and then subtracted umk to split it into two pieces. But then I just use these two inequalities. M sub k is less than m prime, so, or less than or equal to. So the first term is less than or equal to this. M sub k is also less than or equal to m double prime, so the second term is less than or equal to this. But lo and behold, that's what we wanted to show for this step. Right, what we wanted to show for this step was that this guy is less than or equal to this sum, and just by that simple infimum argument, this guy is indeed less than or equal to the sum of those two pieces. Okay, I think there's one or two more slides in the proof, but this is the nice intermediate result. Questions on this infimum argument?
I have no questions. This is sufficiently clear.
Good, good algebra. Um, okay, last slide. Uh, so this, again, we still have to generalize because the whole thing I just showed way back in our plan was that I would do the one more point case, but remember we're trying to prove it for any refinement. So anytime P is a subset of Q. So I just need to say some more words about how this generalizes. So I'll do it for the lower sums, and then in a daily challenge I'm going to ask you to repeat the whole argument for the upper sums. So I'm just not going to do that half. You'll just have to repeat this whole argument that I just gave, basically repeating every step, but doing upper instead of lower and capital M's instead of lowercase m's, and you can do that for one of the consolidation document problems. But okay, what's the last step for the lowercase, which I will do? Suppose Q is any, again, refinement or finer partition compared to P. Then all we do is add one point at a time. So you make a series of partitions. You start with P, which I will call also P sub 1. I'll alias him to P sub 1, if you will. And then you have another partition P2, where you just add one of the extra points that's in Q. Then P sub 3, and P sub 4, maybe up to P sub alpha, where alpha is some number that is the number of points you need to add. And once you've added all the points, that's Q. Okay, well then we're in good shape, because we've proven the inequality between the lower sums for each of these steps in the chain, right? That was the 1 point case we just proved. So certainly the lower sum in the first partition is less than or equal to the lower sum in the second partition, because that's a 1 point difference, which we proved. And you just apply that all the way up to the last one. And then this chain of inequalities taken end to end, I guess I should highlight this thing, proves the lemma. So just to summarize, what we proved is that if you have any pair of partitions and one is finer than the other, then the lower sum in the finer partition is greater than or equal to the lower sum in the coarser partition. So lower sum in finer is bigger than or equal to lower sum in coarser. And that's, again, what our intuition for what this thing is supposed to do would tell us, right? Because we think that the coarse partition means huge jump between adjacent points, right? T sub 0, T sub 1. This is going to have a very small lower sum, because you see that this height is very small. But if I make this partition finer by adding in more rectangles, we expect that this lower sum is going to get bigger, because it gets closer to the true area. So just to summarize, the finer partition is going to be bigger in general. Okay, so I hope you understood that well enough that you can repeat the argument yourself for the other side. In the other side, it's just the opposite way. The upper sums are always going to get smaller. So the one on the right is smaller because Q is the finer one. So the finer one is smaller for upper sums, which you'll prove. Okay, good. Thoughts on this?
I have no thoughts.
Nice. Do you feel confident that you can write out those steps yourself?
Probably not without referring back to this.
Okay, yeah, that's fine. I'll give you the slides and I'll post solutions as well you can refer to. Okay. Alright, so why did I do this huge pain in the ass lemma? I think I've often argued that I like to put all of the hard work in lemmas, and then I like the beautiful theorems to be a simple one-line proof. And this time it literally is a one-line proof. So this is our first major theorem on integrals. And this is actually, yeah, this is the answer to the question, which I trolled you with a little bit back here. Yeah, this one. Because remember, the thing we started with was saying if P1 and P2 are different partitions, we didn't know whether there was a relationship between L and U in general. And now, actually, we know the answer to that question is yes. If P1 and P2 are any partitions, and f is any bounded function, it doesn't have to be continuous. Its limits don't even have to exist. It just has to be bounded. Any bounded function. Then it's always true that the lower sum in partition P1 is less than or equal to the upper sum in partition P2. So again, this guy applies to stars over Babylon, to the function that oscillates on the rationals and irrationals, all of them. So the answer is actually, yeah, just it works the way that you would have hoped in your wildest dreams. Um, okay, so what's the proof then, since this seemed like a very hard thing to prove before? Well, it's very simple. You first make a new partition by just putting all of the points in P1 and P2 together. You take their union, right? So if this guy is this guy starts with, oh, for fuck's sake, the pen keeps breaking. So if P1 was T0 up to Tn, you got a bunch of points. P2 was maybe, I don't know, S0 up to Sn. I just say take the union of all of those. You take all of the T's and all of the S's, and now you're probably wondering, oh wait, didn't you do something wrong here, because the left one always has to be A and the right one always has to be B. So by taking the union, haven't you done something bad, because now the letter A is in that set twice, but remember, sets don't care about multiplicity. These guys are both in the set, that doesn't break anything, so who cares? And right, I haven't written them in order either, but that doesn't matter either. They're just a bunch of numbers. So hopefully you agree, given any two partitions, I can always combine the two of them, and the result is still a partition, because it's still a bunch of points in the interval, and it still has A and it still has B. So I can always do that. But now we have a one-line proof. Here's what you do. You start with the lower sum in partition P1. We proved that for lower sums, a finer partition always has a bigger or equal area. Well, P is certainly a refinement of P1. P has all of the points in P1 and possibly some more, because P came from a union involving P1, right? So P certainly has all the points of P1. So the first step is from our lemma, right? Lemma. The second step is that we know that when the partitions are the same, the lower sum has to be at least smaller than or equal to the upper sum, right? Because this is by the definition of infimum and supremum, right? Same partition, you're adding up a bunch of infima times the t sub I minus t sub I minus 1s. These are a bunch of suprema. Suprema are always bigger than or equal to infima, so this is by def of sup and inf. And now, this last step is from the other half of the lemma, which you will prove in the DC, which is that for upper sums it goes the other way. Again, for P being a finer version than P2, because P again has all the points of P2 and maybe some more, the way it works for upper sums is that the finer guy is always smaller than or equal to the coarser guy. So that's again from the lemma. So I find this is a breathtakingly beautiful proof once you have that lemma. It's just one chain of inequalities. Lemma, lemma, and then one in the middle that uses suprema and infima. And then it's just done. We proved lowers are always less than or equal to uppers, even if you change the partition. Good. Thoughts on the breathtakingly beautiful proof?
It kind of seems like putting it in a lemma of its own was almost unnecessary, because it basically moved the proof to something separate. But I guess having the lemma separate allows you to use that specific little tidbit of information on its own.
Yeah, we'll use that elsewhere. This is very much like in Python. If you're writing a big programming project, and you know there's going to be some reusable feature, right? Like maybe you're, I don't know, when you do the thing to find the lower and upper sums, right? You wouldn't define a function, I don't know, lower sum, and then in that function you would write some code to find, remember for the lower sum you have to find the infimum. You find the infimum, add them up, and then return L. That would be very bad programming, because this step of finding the infimum is something which is highly reusable. You want to abstract that away, black box it, and instead make a separate function which is define infimum, and then blah blah blah, do all the work here, and then instead you just call infimum inside the program, so you're not repeating yourself. That's very similar to the reason for splitting up this lemma, because this lemma about lower and upper sums, this is going to be useful in other contexts, maybe not in this meeting, but this thing is something which you wouldn't want to repeat yourself and do this argument again if you had something similar that was not just the same as this theorem. So so yeah, you might object. You said, okay, this isn't actually a beautiful proof at all. You just wrote a very ugly proof and then chopped off the last step and then said, okay, the first part isn't my theorem. That's some ugly thing. And the last part is now beautiful. So that's very fake. You're just, being a showman. Okay, so fine. Maybe you could make that argument if you like, but I will defend myself by saying that I'm making the first part reusable. Good. Other thoughts?
I have no thoughts.
Okay.
You.
All right. So let's do Act 3. What are we, 1 hour in because we started half an hour late or something? Good. All right, so what's the integral now? First, I want to motivate our definition a little bit. Before I give you the definition, I want to show you why we should be careful about this. So let's go back to one of our favorite functions, this guy who flips on the rationals and irrationals, the table flip function, if you will. So this guy, we recall he's 0 on every irrational function, so you put more dots because there's somehow more irrationals than rationals. He's 1 on every rational point. And now I'm going to ask you a question. Suppose I want to find those lower and upper sums that we just talked about. Right? So I'm going to say there's any point A, which is t0, then a t1, t2, up to tn minus 1. And I'm going to try to write down the lower and upper sums in that partition for this weird function which oscillates. So take a minute to think about it if you want, but what first will be the lower sum for this guy?
Yes, was the question asked?
Yeah, what is the lower sum?
So this is fairly simple since it is, well, the infimum on this range is, allow me to recall, 0, regardless of what your range AB is, to my knowledge.
Yeah, good. So you're saying the definition of this guy is I'm supposed to take maybe the infimum on the first chunk, right? I'm supposed to take the infimum on every interval separately, right? So I take the infimum on the first guy times t1 minus t0. Maybe this is the first infimum, but you're saying the infimum, the infimum on this first guy is 0, and then I add this to the infimum on the second guy, right? The t2 minus t1. But the infimum on this guy is also 0, so I'm just going to add a bunch of zeros, and the sum is going to be 0. So can you say one more word, or explain why do we know that the infimum on every subinterval, no matter how tightly we pack these guys together and chop up this interval, how do we know that the infimum will always be vanishing?
It's being multiplied by 0? Wait, was that the question? Was there a question?
I'm asking, how do you know all of the m's are 0, right? How do I know that the infimum of the set of all f on t sub I less than or equal to x less than or equal to t sub I minus 1, how do I know that the infimum is always 0? How would you prove this?
What was... Okay, I don't know if it is totally related, but I feel like it has something to do with the fact that there is no least upper bound for a set of real numbers.
There's no least upper bound.
Well, real number? Real number, yeah. Are irrational numbers real numbers?
Yes, Q is a subset of R. Yeah, so if we wanted to prove that the infimum on any non-empty interval of this function is 0, then I think what we should say is something like, well, just look at these two endpoints, t sub I and t sub I minus 1. They're both either rational or irrational. But if they're both rational, we've proven that between any two rational numbers lies an irrational number. So that means there's some number in the interval which returns a function value of 0, right? But the same argument applies if either of these are irrational, right? You could do the same thing. If they're irrational, we've also proven that between any pair of irrational numbers lies a rational number, so use that to find a rational subinterval, and then we know that between any two rationals lies an irrational. So the point is that because of this nice thing we've proven way back in chapter 1 that, between actually any pair of real numbers there lies an irrational and also a rational, we know that you can always find a number in this interval whose function value returns 0. By the same sort of reasoning, you could find that on every interval you can find at least one point where the function returns a value of 1. So using that argument, what would the upper sum be?
The upper sum would be, well, it would be t minus 1 minus t0, and we would just, we can write down the sum definition.
Yeah, let's just see what's going to happen.
Plus t2 minus t1 plus t3 minus t2, etc.
Yeah.
No, it's going to cancel out until you get to do tn.
Yeah, this is what's called a telescoping sum.
Oh, wait.
So we have a tn and a t0, which is, what, b minus a.
Wow.
And now that we look back, we would have said, okay, that's geometrically kind of obvious because this is a partition. A partition is just a way of chopping up the interval. And if we just multiply 1 by the length of each of these intervals, which is the width of the rectangle, if I just add up all of the widths of these rectangles and the rectangles partition the interval from a to b, then clearly the total width had to be b minus a, right? I'm just measuring the length of some interval by chopping it into pieces and adding up the pieces. Good, okay. So indeed, the lower sum in any partition is 0, and the upper sum in any partition is b minus a, which is generally non-zero. Good, okay. Thoughts on this?
I have no thoughts on this specifically. Bernadette is asking about Python.
Oh, good. I'm excited about this. Wait, do you want to take a break to answer her, or should we?
No.
Okay. Good.
She was asking, like, how do you keep motivation?
Oh, that kind of stuff. Okay.
Yeah.
Oh, that's
and I'm like, you're asking the wrong person, but,
no, you should form like a
if
little...
you're having fun, there's your motivation.
No, I don't think fun's enough. I think you need people. You won't stay motivated to keep doing stuff unless you're working on a project with someone. Like, I don't know.
Okay.
Well, that's my opinion, at least. Maybe you're different, but for me, like, I would lose motivation to keep working on research if Saab wasn't dropping by the office every day to chat about it. I mean, maybe you would find it more difficult to keep doing calc if I didn't force you to meet and talk to me twice a week or something. So, I don't know. That's my opinion.
So, yeah, people helps, and maybe I should mention it to her. Actually, should I mention... She mentioned not wanting it to feel like work, but is that what it is? Kind of is.
I think it's like a hobby. I mean, if you get together with someone and you're like, if you're coding something fun, like, I don't know, programming competition like Bloomsburg problems or something, and you get together in a group of people, like in the same room coding together, and you're like coding but also kind of goofing off and eating food and having fun, like that's not that different from getting together and playing D&D, right? I don't view it as work. I just view it as academic fun. I don't know, maybe I'm just a nerd though, and other people don't think that.
Thoughts? No thoughts.
No thoughts on me being a nerd. Okay, good. Are you good to go on, or are you still typing?
I am good to go on. I never was typing.
Oh, okay. Sorry. I thought you wanted to answer, but okay, good. So, why did we do that example? So, indeed, I argued that since we can always find an irrational on every interval, the lower sum must be 0. We can always find a rational on an interval, so the upper sum must be b minus a. And this isn't so great because I was trying to make this argument way back in the first part that we're trying, our idea of the definition is to write down an approximation, right? Like the lower sum or upper sum, and then take a limit, in this case the limit as we make finer and finer partitions, which is supposed to make the answer exact. So we were trying to make the approximations better than the partitions. But Now we see that's clearly not going to work in this case, right? You can make this guy as fine as you want. He's still going to be 0. You can make this guy as fine as you want. He's still going to be non-zero and constant. So there is no way we can make the approximations exact, right? Exact in the sense that, I mean, we're going to change the partition and make the answers better. No way to make approximation exact. Okay, so again, this is another example of pathology in mathematics. You write a definition expecting it to behave a certain way, right? I write my definitions of lower and upper sums with the expectation, like, yeah, when I make these guys finer, I'm always going to get a nice answer. And then some ugly dude comes along and says, well, no, screw you, here's a function, and those answers don't get better. So what are you going to do about it? How do you fix this pathology? And as usual in mathematicians, in mathematics, what we do is we do this by, defining the problem away. We cloak our ignorance in terminology. What do I mean by that? If I define the problem away, I say we just pick a new word, integrable, which refers to a nice function, and we declare that functions like this, which don't behave the way that we want, are not integrable. So we say, all right, fine, ugly dude, you came up with something that I don't like, but I'm going to say I want to only study functions that are integrable, which means they do not have this property. In other words, if we are defining an area by this integral, we're just going to say the region under that graph you just showed me, this thing that flips on the rationals and irrationals, is so weird. This doesn't make any sense to assign this an area at all, so I'm just going to throw up my hands and say it doesn't have an area. It's not integrable. That's what we're going to do. Okay, but to do that, we actually have to be precise and say, okay, so to prevent more ugly dudes from coming along with increasingly weird examples, we have to put a very precise definition in stone that will keep all the ugly dudes away. So what's that? Here's the definition. We'll say a real valued function f, which is again bounded, so we're still not talking about things like tangent that go to infinity. You're bounded on a to b, and we say that function is integrable on a to b if the following thing is true. If the supremum of all of the lower sums, so don't get confused, we're taking the supremum, which is the biggest value of a set, or the least upper bound, to be precise, of a set. So we're taking the biggest of all of the lower sums. Right? Now remember, that makes sense, because the lower sums get bigger as you make the partitions finer. Right? So we want to find the biggest, or the least upper bound of these guys. So we want the supremum of the lower sums to be the infimum of the upper sums. Because remember, the upper sums get smaller and smaller as we make the partitions finer. So this is just saying, if I write down every possible lower sum I could get with any partition, take the supremum, the least upper bound of that set, and I get the same answer as what I would get by looking at the infimum of the set of all possible upper sums, then I declare this function to be integrable. And if that is true, if these two things are equal, then, of course, if two numbers are equal, then they have the same value. So rather than writing down this ugly expression and this ugly expression for two numbers which have the same value, which is really just one number, we're going to pick a nicer symbol for it, which looks like this. It's called the integral of f from a up to b. So you just write it with this curly. Okay, so this is critical. This is, I mean, roughly, this is our analog of the epsilon delta from limits. This is the central definition of what we mean by integral. I'm going to take soups and ints of sums. So, okay, thoughts on the definition?
I have no thoughts on the definition. It seems slightly more, I'd say, wordy.
Yeah, I wrote this out very explicitly. P is a partition. Often when in subsequent proofs, I'm not going to write out this whole part. I'll just write the supremum of all of the lower sums of f comma p. And you'll say, what is p? And I said, okay, fine. I mean, secretly this means p is a partition, but I don't want to write this out every time. So to shorten it, I'm going to write this and like just trust that between friends you won't yell at me for not declaring what the variable p is. But I agree. It's a little wordy. It becomes less wordy if you truncate that thing. Good. Other thoughts?
Yes, one thought. I said to Myrna, come up with the ideas, and she came up with a very interesting Arduino idea.
Ooh, that sounds fun. Do you need
A
parts?
robot that threatens you with a knife when you say you want to die.
Very appropriate given her dagger emoji in the status yesterday.
It sounds kind of easy, so I'm actually on board with this, and
How do,
I've spent knives.
but how does it detect when you say you want to die? You need some voice recognition, I guess. Unless there's an I want to die button, like an easy button.
I have throwing knives. Could I make a bot that throws throwing knives?
Sounds like a hard robotics problem to get an actuated arm that throws knives. I don't know.
I know what to do now. Okay, totally unrelated stuff.
Those are interesting thoughts as well, though. Throwing knives. Good. Okay, so I'll do, I think, one more important proof. But, oh, first, okay, we should have a challenge to use this definition. So, why don't we let f of x be some constant function, right? So fix some number c, and here's f as the constant function, and I'm also going to pick 2 points a and b. Now, we certainly expect that the area under this thing should be, well, the height is c and the width is b minus a. So if our definition that we just made is any good whatsoever, then we should be able to prove directly from that definition that the integral from a to b of f is c times b minus a. So let's do that. What should I do if I want to prove that f is integrable on a to b, and that the value of that integral is this thing?
First, we want to show that this is integrable, so we need to refer to the inequality that I have not yet memorized. So we want to somehow prove that the supremum of L of fp such that p, etc., or, well, L of fp for all p, and inf of, well, supremum of u of fp for all p, I believe is the case. Can we say for all p? It sounds reasonable.
Yeah, you could say for all p. Or sometimes I often say this: the supremum of the lower sums is equal to the infimum of the upper sums, and just don't say any. I mean, implicitly I mean over all the p's, but it gets wordy. But yeah, so we want to prove this. So
Okay.
how do we prove? Well, first of all, what is this set? So let's just start on the left side. So we want to write down explicitly what is the set of all lower sums such that p is a partition. Well, I claim that this is a very small set. What is this set exactly?
I believe that since this is a constant function, we know that regardless of our set p, it is going to have the, I guess, well, it's going to be a consistent height. And therefore, we can simply have it be bounded by AB.
Not just bounded, it's going to be exactly equal to. So let's just compute it. Let p be any partition, any sum, any collection of points t sub I, right? So what's this going to be? It's going to be the infimum of the function on the first subinterval, right? So the t0 up to the t1. But what is the infimum of the function on this interval?
The infimum is going to be C.
Yeah.
I believe.
That's the infimum on any interval, right? So
Yeah.
if oops, wrong way. T1 minus T0. Now we have the next one, which is maybe T2, and the infimum is again C, so C times T2 minus T1 plus dot dot dot, and then you got the last one.
Isn't this familiar?
Yeah, minus Tn. So now you just pull the same trick. You say, all right, well, fine, all you've done is multiplied by C, but this guy still telescopes. The T1 cancels the T1, the T2 cancels the T2, all the way down to here. Oops, I put these indices wrong. Tn minus 1.
If anything, you can factor out the C and argue it that way.
Yeah, if you factor out the C, it's the same sum as before, right?
Yeah. So it's simply going to be CTN.
Yeah, minus the t0. But by definition of
Right.
partition, that guy has to be B, this guy has to be A.
Whoa.
So yeah, it's not rocket science, but notice that that did not depend on the partition. That same calculation applies for every partition. So if I want to write down the set of all lower sums for every partition P, what is that set?
That set is what? I missed a thing.
Well, let's see. So we're writing down the set of all lower sums in any partition. Then I just told you that in any partition, the lower sum is this. So, so what is this set then?
Like this has to be painfully obvious, and I'm not getting the question.
Let me ask a different question. So, what is the set of 0 times the number x for all x in the real numbers? So I'm going to write a single set which contains all of the numbers you get by taking any real number and multiplying it by 0. Must be a
It's
pretty
going
big
to be a
set,
single. What?
right? Must be a huge set, right? There's all the real numbers. No, what is the set?
It's zero.
It's
Okay,
0.
so it's a single point.
Yes, indeed. So this is
So
the points do not count multiplicity is what I'm getting at here.
that makes much more sense. So it's going to be CB, well, C times B minus A, or CB minus BA. I mean, CB minus CA, however you want to word it. Words.
Yeah. I don't want to distribute. So yeah, this is the single element set which consists of the single real number c times b minus a. Okay, good. I don't. Hopefully, you don't need to see this repeated, but it should be hopefully pretty clear how you would prove this. That just go through the same thing and argue that for the upper sums, now I just say different words every time. I take the supremum on every interval. The supremum of a constant set is that constant. So the supremums are still c's, the sums still telescopes, or if you prefer, you factor out a c and apply the same argument. So this is again a single element set. Okay. So now, what do we have to prove? Oh boy. We have to prove that the supremum of the lows equals the infimum of the highs. Well, alright, fine. So I will ask you, what is the supremum, the least upper bound of the set which has a single real number, c times b minus a?
I think it's C times B minus A.
Yes, it's certainly an upper bound, and it clearly is the least upper bound, because any smaller upper bound would be smaller than the one thing. Likewise, what is the infimum of this singleton set?
That is also C times B minus A. And therefore, the integral of... How do you say that?
The integral of f from a to b.
Okay.
Sometimes people write this as integral of f dx. Why do they do that? Well, this is supposed to look like the s, the squiggly s is supposed to look like a sum, so this is kind of like a sigma, but it's smoother because it works for smooth curves. So people like to write, the sum of all the heights, which are the f of the maybe yi's, times the widths, which are the delta yi's. That's like the difference between the t sub 0 and the t sub 1. This is some delta x or delta y. Maybe I used y because I didn't want to use the same letter twice, but maybe I should use the same to make it clear what the notation is. So people like to think, oh, well, this integral is really like a sum where you chop it up into different pieces and you multiply f at that piece times the delta, which is the width. But then when it turns into an integral, I want it to look similar but use a different letter, so I use a d instead of a delta. It doesn't mean anything. The dx is just put there for convenience if you like to think about that. So mathematicians often write it without the dx. They just write integral of f. They say, I don't need that cutesy shit you just put on the end. I just mean the integral. But whatever. Okay. I'm letting my biases seep through again. Okay, good, indeed. So as you said a moment ago before I went on the diatribe, you said we have proven that these two things are equal because they are both c times b minus a. And that means, by definition, if the two things are equal, the thing they are equal to is the integral, which is indeed the area. So for constant functions, as a sanity check, our new definition of area coincides with the old definition of area. Good. Thoughts on this?
So I guess I totally missed all of your bias by thinking about whether Python can be used for robotics.
Uh, that's a good question. I've never used it for robotics. I suspect libraries must exist. Uh, I can look into it if you want, though.
I have no further thoughts or questions.
You sounded hesitant at the end of that sentence.
I am not hesitant.
Okay. Okay, so yes. Once again, the answer was that if P is any partition, the supremum and infimum on any subinterval is C, because it's a constant. So if you add up all the lowers, this guy telescopes and you get B minus A. If you add the uppers, same thing. Supremum of a singleton set is the thing. Those are two equal quantities, which is by definition the integral. Good, so we can integrate constant functions, or we can find the areas of rectangles in a slightly more precise way. Okay, so last thing for today is this proof. So this is another nice theorem because you may have noticed from going through this argument that these supremum and infimum things are pretty hard to work with or you can imagine at least, they're pretty hard to work with when you get bigger sets, right? So in this simple example where it was a supremum of a one element set, we could just do that. But you could probably imagine that if we want to prove things like, we want to prove that all polynomials are integrable, right? So if I want to prove that every polynomial is integrable, which is true, you can imagine it's going to be pretty challenging to work directly with supremum and infimum of a bunch of polynomial things, right? Because this will be a supremum of a complicated set. So we want to prove a different characterization or a different condition, like a test we can apply to a function to see if the function is integrable, that is easier than using sup and inf. That's what we'll do. This is the reformulation. Okay, so here's the theorem. Again, f is bounded on a to b. Then we claim f is integrable using our old definition, so it satisfies the usual definition on a to b, the interval from a to b, if and only if, for every epsilon greater than 0, there exists a partition, p, of a to b, such that the difference between the upper sum and the lower sum is less than epsilon. Notice that this is very similar to the epsilon delta definition for a limit, except for two things. One, you have to, the guy can come and hand you an epsilon, so handed any epsilon, we have to find a partition rather than a delta, right? In the limit definition, someone hands you an epsilon, you cook up a delta. In the integral definition, someone hands you an epsilon, you cook up a partition p. And the second thing is that we don't need absolute values here. In the, f of x minus f of l is less than epsilon. In the usual thing, we were trying to argue that the distance between the function and L, the distance was less than epsilon on either side. So there we needed an absolute value, because it could be bigger than or lower than the thing. But in this case, we don't need the absolute value, because upper sums, as we proved, are always bigger than lower sums. For any partition, in fact. So this is the definition we're going to prove. You can't define things two times, right? We already defined it, so if we want to use a different formulation, we have to prove it's the same as the old definition, because otherwise we just made two different definitions and we're inconsistent. Okay, so I will do the proof. I'll prove, well, first, before I start the proof, I will ask, is the idea of this theorem, this characterization of integrable, clear?
I'm reading it closely to make sure that I understand everything.
Okay, good.
This is all clear.
Okay, nice. Just one comment is that you can, if you want a different way to think about this, this is kind of like saying the limit as the size of the partition goes to infinity. You can actually make this precise. We're not going to use this definition. But if you like, you could think that this is the limit as you make it a very fine partition, that the upper sums approach the same limit, I'm not going to write all those words again, of the lower sums. That's a different characterization. This is nicer because I don't have to define what do I mean by size of partition, but if you like inside your head for intuition, you could think this definition is just saying that, as my partition gets super fine, the upper sums approach the same value as the lower sums, and that value they approach is the integral. Okay. All right, so what's the proof? Well, I said if and only if, so I have to prove two things. I have to prove the forward direction. If f is integrable with the usual definition, it has this new property. And I have to prove the backwards direction, that if f has this new property, then it's integrable. So, okay, let's do actually the backwards one first. So that means I can assume that this condition is satisfied. I have to prove that the old condition, the sup and inf shit, that is satisfied. So how do we prove that? Okay, suppose it's true that for every epsilon I can find a partition such that the upper sum is within epsilon of the lower sum. Now, by the definition of sup and inf, this is where I'm being sloppy. This is the set of all upper sums with the property that p prime is another partition, right? So I'm being sloppy, but this is the infimum of the set of all upper sums f of comma p prime such that p prime is some other partition. So this is running over all partitions. Okay, so by definition, infimum is the greatest lower bound. In particular, it is a lower bound. So it must be, whatever this infimum is, it must be a lower bound for the set of all of the upper sums. So the lower bound must be less than or equal to any element in the set. So the infimum is less than or equal to u of fp, where p is the partition I just got using this assumption. Alright, same argument. If I take the sup of the lower sums, sup is the least upper bound, therefore it's an upper bound, therefore it's greater than or equal to everything in the set. This guy's in the set because p is a partition, so this guy's greater than or equal to this guy. Okay, well that's fine, because now I'm just going to kind of subtract, or I'm going to do some algebra trickery. So look at this line at the top. This is saying the u minus the L is less than epsilon. So now I'm going to say, okay, well if I make the first guy smaller, how do I make him smaller? I replace that u by some other number which I know is less than or equal to the first number. So if I replace u by the guy on the left, which is smaller than or equal to him, then the left side can only get smaller, so it's still smaller than epsilon. Okay, good. Then I do something else. I replace L by something bigger. What's the bigger thing? Well, the supremum is bigger than L, so if I replace L by something bigger, then I am subtracting a bigger number on the left side, which makes it smaller. So if it was already smaller than epsilon and I subtract a larger number, it's still less than epsilon. So that means that this new line, which is just replacing the first term by something smaller minus something bigger, this must be smaller than the old thing. And in particular, it must still be smaller than epsilon. Okay, that was a tricky step, but do you see what I did in that manipulation? That's a little slick argument.
This is all clear.
Okay, good. Alright, so fine. So that means that this thing is true, but notice that now nothing on the left side depends on p, right? This is infimum over all partitions, supremum over all partitions. So this is independent of p, which means I can run this argument for, whichever partition p that I got. But I got the partition p by invoking that, I had some epsilon greater than 0 and found a partition p with that property. So if that's true, oh boy, and my muting went off on Slack. Okay. If this is true for every epsilon greater than 0, I can run this for every epsilon greater than 0 and get this line down here independent of p. That means the thing on the left side, this difference, is smaller than every real number epsilon greater than 0. There is no smallest positive number in the real numbers. If the thing on the left is smaller than every positive number, and it's also non-negative, then the left side must be 0. Right? 0 is the only non-negative real number, smaller than every positive number, which is very easy to prove, actually. But okay, so fine. If the inf minus the sup equals 0, that just means the inf equals the sup. And that's what we wanted to prove for the first part. Right, because if the inf of the uppers is the sup of the lowers, then f is integrable. Or if you prefer, if the bottom of the tops equals the top of the bottoms, then f is integrable. but I don't want to say that sentence again. Okay, thoughts on the first half of the proof?
This is all clear.
Okay, good. Okay, now we should prove the other direction. So now we have to prove if f is integrable, then we have this epsilon stuff. So suppose f is integrable, which by definition means the infimum of the uppers is the supremum of the lowers. So if this is true, then this means that we can always give an... maybe back up. So, all right, suppose the top part is true, and you hand me an epsilon greater than 0. I'm just running the argument from before backwards. If then these two numbers are equal, then that means the infimum minus the supremum equals 0. So it's certainly less than any positive number epsilon. Maybe I should have put an additional step in here. The infimum of all the uppers minus the supremum of all of the lowers. Maybe I want the other way. Yeah, why am I doing that? No, this is what I want. This thing equals 0 by assumption, which means it's less than every epsilon greater than 0. So if the infimum of the uppers minus the supremum of the lowers is less than epsilon for any epsilon, then that means that since this guy, this infimum, is the greatest lower bound, and this guy is the least upper bound, then I can always find an element in the set, maybe a p prime for the first guy and a p double prime for the second guy, such that this inequality holds. Why is that? Well, if I couldn't find such a p prime and p double prime, if there were none such, so that this guy was always bigger than epsilon, then that means I could have found a higher lower bound here, or a lower upper bound here, with the property that this thing would have been less than epsilon, because the infimum is equal to the supremum. So it's running the reverse of the previous argument, right? I'm now realizing that I wanted to assign this as a daily challenge exercise to prove that you can convert infima and suprema statements into a statement about finding an epsilon, but I never assigned that. Maybe we should do that as an exercise, because I wanted to now invoke that result here and we never proved it. But okay, yeah, let me make that a daily challenge. But you'll see that hopefully it's intuitive. Maybe the proof isn't clear, but it's intuitive that we should be able to do this. You should always be able to find representatives of the set with the property that this difference is less than epsilon if the infimum and supremum satisfy this condition. So okay, well we'll show that more carefully. But it's true that for any epsilon I can find partitions with this property. Now, the thing that I wanted to show to complete the second half of the proof was not that there exist two partitions, p prime and p double prime, with this property. We need to show that for every epsilon there's one partition with the property that the upper in that partition minus the lower in that partition is less than epsilon. But okay, that's not hard. We just need to take these two partitions and convert them into one partition. And there's a very simple way to do that. You just take the union. Right, so I union all of the points in this guy with all the points in this guy, and then we use our beautiful lemma again. So now my attempt to defend myself in putting the ugly shit in the lemma is coming back to the fore, because now we're going to use that lemma that whenever you have a refinement, that is a new partition P which has all of the points in some other partition, then the upper sum in the finer partition is less than or equal to the upper sum in the less fine, the coarser partition, and the lower sums are backwards, right? The lower sum in the finer guy has to be greater than or equal to the lower sum in the coarser guy. So if that's true, then again, let's just run the same argument. Start with the thing on the left, down here, and now say, all right, well, this guy, oh, sorry, that's not what I'm doing. I'm starting with that in the middle. There we go. We know this guy is less than epsilon, so that's already true. But this guy on the left, in P, well, the upper part, this guy is smaller than the upper part in the middle guy. So in going, I'm saying this poorly, in going from the middle part of this inequality to the left, I have only replaced the first term by something smaller, right? Because we know u in P is smaller than u in P prime. So I've replaced u by something smaller. and then I've subtracted something larger. So now I'm subtracting L in P, which is bigger. So the thing on the left is reducing the positive part and increasing the negative part, so the thing on the left must be at least smaller than or equal to the thing in the middle, but we know the thing in the middle is less than epsilon, so we've proven that there is one partition P such that this difference is always less than epsilon. And that proves it the opposite direction. So this new epsilon nonsense is actually exactly the same as saying the supremum of the lower sums is the same as the infimum of the upper sums. Okay, sorry, I botched this last part a little bit, but I think it'll make more sense once we work through the soup into stuff. But okay, thoughts on this?
I have no thoughts on this. This is all sufficiently clear.
Okay, good. I think this will be kind of like a second, I don't know how to say it, like a return to the proofs of epsilon delta stuff. I think when people go through theoretical calculus, they see epsilon delta stuff in the limit section, and then they just think it's the hardest thing ever and cry. Then they go through derivatives, and they come back to integrals, and now it's like, their second time in the ring, and they say, okay, yeah, this is still very complicated. I have to do all these epsilon delta proofs, but it feels much easier the second time because you've kind of won your stripes doing epsilons and deltas. So even if maybe it's a little challenging to write proofs like this, which you'll do a lot of in this chapter, I think it should be more familiar now that you've had some experience with it.